hello everyone. My name is Junchao Chen. So that it is my honor here to try to show you of our currently TETRISC SoC, which is a fault-tolerant and also self-adaptive quadruple system. So that for this project, it's also be a part of Skill for H. So, not working. OK, I can be here. OK, so that as you could know that as currently as technical scaling, that for this safety and mission critical applications currently facing more and more reliability challenges here. So that for a lot of hardware that they require to provide of a really high reliable, so that how to harden your circuit. And that normally for a designer, you usually consider of these two phases. And at first, at this on the design phase, you can try to deploy for a lot of this one special of these technologies, for example, like some radiation hardened technologies, and also try to harden it through hardware, software, and so on. And also, just during of this runtime, and you could also need to know what's this current status. So it means that you also need to try to add a lot of on-chip sensor and try to analyze of this real-time reliability status. So that brings to our main target of our TETRISC here. So that as you know that currently we have a lot of existing open source RISC-V design here. And also for our part, on our IHP part, that we have a lot of this existing like these on-chip monitors and how to analyze of this system reliabilities, and we consider possible to combine together and to provide and try to convert of this existing open source RISC-V SoC into one adaptive, high reliable adaptive system. So for this target that we propose of our first quadruple system, for this so-called of this TETRISC architecture, as you can see here, for this TETRISC architecture, that's based on of this single core architecture from ETH Zurich of this Papissimum, so that we firstly try to convert of this single core system into this four core system, and also we try to add of this on-chip sensors, and also try to add of this smart central framework controller, try to analyze of everything, and to achieve of this dynamic trade-off between the reliability, performance, and the power consumption. And also for the design of this chip, it's be targeted for this critical edge computing. So let's go into a little bit detail here. As I mentioned that we have a lot of these on-chip monitors. At first, we have of this radiation monitor that we use of this on-chip SRAM to take account of how many faults happens. And also, we can also to use this faults data to analyze of this radiation condition and to predict what could happen in the future. And also, we have two types of this agent monitor. One is for head carrier injection. Another is for this MBTI. And also, we have we also have one analog temperature monitor here. So how to combine? We design this hybrid framework controller here that we collect of this all these informations, so that for our focal system under this default situation, focus under of this high performance mode, it means the focal to run of these 4 different tasks. So that when some special situation happen, we can very fast and very easily to active of these 2 call to run the same task, and the 3 call to run the same task, and the 4 calls to run the same tasks. So I would like to show you of how it's actually working, but wait a second. I'm not so sure why it's still not ready now. OK, I could still need a little bit time of it, and yeah, sometimes it's very time consuming. Let's speak a little bit much more about here. I hope he's ready. Okay, so how could we do it? And as you know, that for a lot of this reliability things, that it have of this different kind of standards. So at this design phase, we try to analyze of these standards, and so that we can know according to our on-chip sensor information and how many faults happens, just under certain condition, which kinds of operation modes we need to deploy then. Let's hope, and I'm a little bit surprised, still working here. Let's go into a little bit of that, since what I want to show you. Maybe later you can see some data here. So that when it's actually power on, that at here, I try to show you of this on-chip sensor data, which operation modes it's running, what's the current temperature of this core, and also how many faults currently is being detected. So that what I intend to do later is try to inject some faults here. So you can somehow to say for our fault codes here, and initially, it will try to run 4 different tasks after some time, and you will also to see what's its current agent status of that call. After some time, I inject the fault. You can see how this cause operation modes to be automatically to convert it. Maybe it could still need some time here for. I'm sorry for that. I think it's really need additional. It's usually take around 3 minutes for it, but not so sure that probably that heat could somehow to affect this hardware connection line. That I hope it can be fine. So let's do it a little bit short. I can talk more. On the other part, let's just assume now everything is working, and also I would like to show you about our future. And for this current chip is already be taped out under our 130 nanometer technologies. Currently, we are under of this skill age phase 2. So it means that we try to upgrade it of what we already have. We have of these 2 targeted here. And at first, that for these 4 cores, they are not so standard cores anymore. That we want 1 core to be fully hardened, which is to use of our triple model redundant library, and also 1 core to be selective hardened, which means that we use of this artificial intelligence ways here, try to analyze of your hardware and only to pick only certain part, try to harden it. And also for our on-chip sensors, we will also try to upgrade it. And also, we intend to do of these two different type out. One is to use of this standard library, and for another one, it is very special, as I'm showing here, that we try to use of our IHP 113 PyMOS open source PDK, so that I will also try to advertise here. Currently, everything is already be open sourced, so that if you are looking for something of this open PDK and also for something similar to Skywater, you can always come to us. And also, we will also try to enhance of this whole performance. Yes, and also for our design is also to be intended to do of this laser-based photo injection and also high ion-based injections here, try to analyze how hardened that it is. Why is this time? Oh my God, it's actually something wrong with this heat of this.
Okay, so
I will try it again.
We're running a little bit of time now. So
yeah,
maybe
I know.
Thanks, Junchao, for now, and have some questions. I don't know. So thank you.
Yeah.
Sure.
Yeah, okay. I'm truly sorry for this, but it's really strange that it's really strange that why it's not working.
Yeah, that's the problem with live demos. You always have that.
Sometimes maybe that time.
Maybe the falling down was a little problematic. So if there's no questions, there's one question. Yeah.
Hi. So the Open PDK library is open source, but the code of the peripherals and all the open road flow is also open source?
Yes.
Can you share the link?
Yes, and for this whole design, as I mentioned at first, that our fundamental of the design is just from this ETH Zurich. So it means as you mentioned, of this I2 LSP, everything is already be open sourced. So,
okay,
yeah.
Thank you.
Okay.
Okay,
so
thanks a lot, and I'm sorry for this. Maybe after 1 year, I think I will be here again and try to show you.
okay, so thanks also to all presenters, all universities, and also to Eva Quintauris to allow those university programs to show the demos. And as I said before, at 3 p.m. we have 3 more demos, so come by then. Thank you.